So, I welcome you here for this NPTEL course on earthquake resistant design of foundations, and this is the fifth lecture on this course, which is on cello foundation. As we discussed the course in 5 module, and we are under the second module, which is on cello foundations. Under the second module, we are discussing the chapter second, which is bearing capacity and settlement. We have already discussed in the last 2 lectures in detail about bearing capacity and about the settlement also. In today's lecture, we are going to discuss some of the numerical examples related to bearing capacity as well as settlement. So, let us in this numerical examples are for both cases, that is for bearing capacity and settlement. So, let us have the first example, which is exclusion in bearing capacity of cello foundations, and in this example what is required to determine the ultimate bearing capacity of a strip footing, which is 1.5 meter wide and its depth is 1 meter. So, that means width of the footing is more than the depth of the footing. So, it is under the category of cello foundation, and footing is resting on dry sand, saturation sand with unit weight. So, this is here resting on a dry sand, and this should be deleted, this is not there, saturation is not there, with gamma d equal to 17 kilonewton per meter cube is the unit weight, dry unit weight, and the angle of internal friction, effective angle is 38 degree, and being the sandy soil, C is this cohesion is 0. So, the ultimate bearing capacity Q u need to be calculated using Tarjagi's theory, that is the first problem of this example. Once the Q u has been determined for this case, then we need to see the effect of water table. What happens to the value of Q u when the water table rises and reaches at a depth of 0.5 meter below the base of the footing, that is the one case, and another case when the water table further rises and it is above 0.5 meter from the base of the footing or at 0.5 meter below the ground level. Other data given are here, that assume saturated unit weight as 20 kilonewton per meter cube, unit weight of water 10 kilonewton per meter cubes, and for Tarjagi's theory, when you assume the angle of internal friction 38 degree, the value of n q equal to 60, n gamma is 75, this is n gamma, and then we need to, with this data we need to start the computation. So, let us first without the effect of water table, when the water table is very deep. So, this is the situation here. So, you have to see the figure, in this figure B is the width of the footing and df is the depth of the footing, simple, and according to Tarjagi's theory, the ultimate bearing capacity is given by this relation Q u equal to C n c plus Q n q plus 0.5 gamma B n gamma. Here being granular soils, C equal to 0, while the value of Q is, we need to remember that Q is in this case is nothing but surcharge. So, surcharge will be because there is no water. So, gamma d into df, where gamma d value was 17 and the depth of footing was 1 meter, df was given 1 meter and B is given 1.5 meter. So, this is the case here. So, the Q is comes out to be 17, then using the equation, this equation we calculate C once you put the C equal to 0, the first term is 0 and the second term 17 into 1 for Q and df, df is 1 meter, n q is 60, and then for 0.5 gamma 17 into 1.5 is the width and then 75 is the value of n gamma. So, you get the value, answer comes out to be 1976.25 kilonewton per meter cube. So, this is answer. This was the case when the water table was very deep means water table was more than from the base of the footing. Suppose the water table is here, in this case, then this need to be, this depth need to be, this is greater than B. So, in this case no need to apply the correction for water table. But when this water table rises above and when it goes towards the footing, then what is the corrections. So, this is given in this case when the water table rises and it is located at a depth 0.5 meter below the base of the footing, which is typically denoted by dw dash prime. So, if you see in this case, then we can apply the correction for water table, and this correction can be applied by two methods. One is called exact method, another is called this approximate method. So, exact method means where you calculate the value of unit weight applied in this case for the terms, these different terms, what should be the unit weight of soil, and that you calculate in exact sense and then apply, and that is the better way than the approximate method. And I can tell you that this will be easier than the approximate method. Even name is approximate method, but that is not going to be simple. So, let us talk about exact method. In case of exact method, ultimate bearing capacity is given by this relation. We already dropped the C, once we said C equal to 0. In the ultimate bearing capacity term, you have only two terms, that is gamma df into nq plus 0.5 gamma b n gamma. In these two terms, there will be no effect of water table in the first term until the water table goes above the base of the footing, while in the second term there will be effect if water table rises. And so, for the second term, the have calculate the effective unit weight using this relation, and effective unit weight gamma is gamma submerged plus dw dash divided by b gamma t minus gamma. Here you need to understand that gamma submerged is nothing but gamma saturated minus gamma w. The value of gamma saturated is already given 20 to you and gamma w is 10. So, gamma submerged is 10 kilonewton per meter cube, and once you have this 10 kilonewton per meter cube, then you have gamma submerged plus dw is already that is the depth below the base of the footing 0.5 divided by b 1.5 17. So, you calculate 12.3. Here while you calculate this value, effective value of gamma, you need to make sure that this value is more than gamma submerged and less than gamma t. It cannot be more than gamma t. So, what I suggest that check, apply this check that your this gamma submerged, gamma is greater than gamma submerged and less than gamma t. So, this check need to be applied for all when you apply the correction for what on the unit weight. Once you got this corrected value or effective that is let us say value for the unit weight, then put in this equation, and as I said, because water table is located below the base of the footing. So, only this term get affected while this term is not get affected, and then you put the values these numbers, and then answer comes out to be 17.4 kilonewton per meter square. And naturally, as the effect of water table, your bearing capacity is expected to decrease. So, the value which you obtain final number should be lower than the value which you have calculated in the previous slide. That means, this value need to be this was 1976. So, this is okay, this is less than 1976 kilonewton per meter square. So, that means okay, this cannot be more than that. If it is coming more, then you have done some calculation mistakes. So, that need to be seen. Now, this was the case when water table was rises, but it was still below the base of the footing. Now, let us see the next case when the water table further rises and it goes above the base of the footing, which is here above the base of the footing. So, in this case here the location of water table is above the base of the footing, and it is at a depth 0.5 meter from ground level, and depth of the footing is in this case is 1 meter. So, that means it is here. So, what you have in this case, you could see that now because the water table rises above the base of the footing. So, both the terms will get affected, but the last term gamma for the last term is in the second term is gamma submerged, which is given 10 kilonewton per meter cube. Now, let us talk the what is the effective in the first term, and that is calculated here. We do not use d dash. So, in this case it will be better not to use this dash is not used anyway. So, simply it is without prime value. Once you have this, then you can calculate the value of gamma t minus gamma, and here one need to be understand that this ratio is dw by df. In the last slide this ratio was dW by B, dW dash by B. So, the ratio was divided by B, but now this is divided by dF. So, this is the common mistake normally you do. So, you have 10 this once you calculate. So, the first term gives you 13.5 and the second term is set gamma. Again you need to make sure the value is, this value is in between, it should be more than gamma submerged and it should be less than gamma T, that need to be understood. Then when you put the numbers, then you get 1372, because now water table has rises. So, one need to make sure that this value is even lesser than what you have calculated in the last slide, that was 1714. So, this is less than 1714 kilonewton per meter square. So, that is okay. So, that check need to be applied. This was using exact method, but once you have what we called approximate method, in this case the next slide talks about approximate method. What you do in approximate method, you apply the water table corrections using the factor RW dash. So, in this case, in the first case when the water table is rises and it is just below the base of the footing at 0.5 meter, then using this relation you can apply the correction factor for RW dash come 0.67 and then this equation can be used. But one important issue here in this equation, because only the second term will get affected now, the value of gamma, neither it can be gamma submerged nor it can be gamma saturated, rather you need to calculate the value of gamma depending on your location of water table, and the gamma should be calculated the average values between gamma submerged average values between gamma T and gamma saturated. So, for example, water table in this case was 0.5 meter below the base of the footing. So, up to when the water table is not there, it is you have this dry unit weight. So, 17 into 0.5, then you have saturated unit weight plus 20 into 1.5. So, this gamma need to be used 19 in this case here, and then once you substitute the value you get 1736, and this value which you are getting is little higher than the value which we have obtained from the exact method. Exact method, this number have come 1714. So, this 1714 this is, if you compare this with 1714, earlier obtained answer was 1714 kilonewton per meter square. So, that means this is higher. So, that means it is not conservative. So, it may be not good on the safer side. So, it is recommended that to use the exact method rather than approximate method. The same was the case if you compare for the second case, when the water table further rises, then you could have this number here, for that is what we call the B case. In this B case, as we discussed earlier, both the terms will get affected and the RW dash this prime will not be there, and as a result you have 0.75, and for the second term you can find the value of gamma effective 17 into 0.5 plus 20 saturated, and this value should be 0.5. So, this you get 18.5, and once you put all these numbers here, then you get 1395. Again, if you compare these numbers which you have obtained from the exact number, which was for exact case, the value was here 1 minute, this was 1372. So, if you compare this number with 1372, which is coming 1372 kilonewton per meter cube per meter square. So, again this number is quite high, a little higher than this value. So, it is not on the safer side. So, my recommendation is to use the exact method rather than approximate method to calculate the effect of water table, and which will be simpler also. So, then let us after discussing the effect of water table on the bearing capacity, ultimate bearing capacity, let us discuss the next example, which is on continue on bearing capacity of cellar foundation. But earlier what we have used was completely a sandy soil, granular soils, the value of C was 0. In this case C is not 0, rather there is effect of drainage. So, let us see that how the drainage changes the bearing capacity, or what is the effect of drainage. So, the ultimate bearing capacity Qu of a strip footing which is 2 meter wide and base at depth, it is lying at a depth 1.5 meter. So, means simply what we see in this case, B which is given, the value of B given to you is 2 meter and df is given 1.5 meter and B is greater than df. So, this is shallow foundation. Saturated unit weight of the soil is given 20 kilonewton per meter cube. Now, when you have undrained condition, your phi u was 0 and you have only cohesion, that is Cu. When you have drained condition, then because as a result of drainage you got some internal friction, but your the value of C get reduced, the phi becomes 20 degree while C becomes 10 degree. So, in these two conditions, what are the bearing capacity we are going to find? As a result, you will see the effect of drainage. So, let us see the first case when, and this is done using like that. So, let us have the first case. In the first case, and it is here undrained and drained loading conditions can be using the total stress and effective stress shear strength parameters. So, for undrained loading condition we will use the total stress parameter, while drained condition you need to use effective strength parameters. For undrained loading condition, when phi equal to 0, you have Tarjagi's theory, you know that NC is equal to 0.7, 5.7 while NQ is 1 and N gamma is 0. So, the value of Qu ultimate bearing capacity is Cu Nc plus Q. So, Cu is 5 given 20, Nc is given like you have this and let us first, what is Q? Q is surcharge and surcharge is coming from the top, which is total 1.5 meter, but out of the 1.5 meter the location of water table is given to you, and if you see in the last slide the location of water table is with its base of depth 1.5 meter below ground. So, depth is given and for the natural water table is, yeah, it is written here at 1 meter below the ground level. So, we should not miss this 1 meter below the ground level. So, below the ground level total depth is 1.5 meter. So, the location is comes somewhere here, if this is 0.5 meter sorry this is 1 meter. So, then in that case it will be this will be somewhere here, this is 1 meter below the ground level, and until you have the water down you have the such this. So, the Q will be you have when up to 1 meter you use the total weight, that is 20, but below the water table it will be submerged. So, that is Q will be 20 into 1 plus 10 into 0.5. So, 25 kilonewton per meter square, and once we put all these numbers here, then you get the value of Q equal to 253 kilonewton per meter square. But in the second case, in the B case, when you have the drain loading conditions, that is this is the B case and this should be this should be treated as a B. Drain loading condition, when you have phi equal to 20 degree, you have the value of Nc, Nq and N gamma. These factors are from Tarjagi theory for 20 degree. Now, in your equation you have C Nc Q Nq plus 0.5 gamma B N gamma. Earlier the third term was absent, simply because N gamma was 0, and in this case the value of Q is surcharge is same as before 25. Now, we put the number here, and this number we do have the C, we do have also Nc, Nq and N gamma, and then we put all the numbers, then you get this value 420, which is greater than the value which has been calculated in the last slide. So, this number was 253. So, this is greater than 253 kilonewton per meter square. So, as a result, what is our outcome? It says then when you drained out the water, then the ultimate bearing capacity have increased, and the simple reason being that because now you got some friction, angle of internal friction have come as effective parameters compared to that, though there is a decrease in the value of C. So, that under drain loading condition is higher than the undrained loading condition. For drained loading condition is higher than the under undrained loading conditions. Therefore, the bearing capacity analysis for a clays should be carried out invariably under undrained loading condition. Why? The simple reason here, because for this we want to be on conservative side. So, the answer for undrained loading condition is QU is smaller. So, that will be there. So, now let us talk about another example which is on the settlement of cellar foundation, and in this example what you have been given? You have been given the data of a plate load test. In this table, and these data are the conducted plate load test on a 60 centimeter square plate. That means, your the value of BP is 60 centimeter, thus, and depth of the footing df is given 3 meter. So, in this case df is 3 meter on a which extend up to, and settlement of foundation is 3 meter by 3 meter square size of the footing, that means Bf equal to 3 meter. These are the data given. Carrying a load of 110 ton and located at a depth of 3 meter below the ground surface. So, the depth is common. In the plate load test, the plate is kept at the same depth where you want to that is the depth of the footing df. Now, using this data, what we do? First thing is that we prepare a load settlement curve which is shown in the slide. So, you could see that this load settlement curve is not linear, rather initially when you increase the load, settlement little bit increases. However, after that the value of settlement increases exponentially. So, as a result you can divide this graph into two component. One component is initial component, and if I draw an asymptote here, this is this, and the last part this is asymptote, and both are meeting at this point, and the load intensity corresponding to this point is called QUP, which is shown in this figure. So, what you have, the load settlement curve is shown in this, and load settlement load intensity shown in this case is in ton per meter square. After this, once you have this plotted this chart, then this is used for further calculation. How this is used? The value of load intensity of the foundation is total load divided by the area of the foundation, which is 3 meter by 3 meter. So, you get 12.2 ton per meter square. For this value of 12.2 ton per meter square, you get the settlement from this chart. So, this is 12.2, and for this value you get this is here. So, you get the value load intensity from here directly, and load intensity sorry, this is other way, load intensity is given to you 12.2. So, 12.2 will come somewhere here, and for this load intensity you get the settlement, and if you get the settlement, this is 5 mm, or otherwise directly from this table load intensity is 12.2. 12.2 will be between 10 and 15. So, the settlement will be between 4 into 7.5, and interpolation gives you the value Sp equal to 5 mm. So, the settlement of plate is 5 mm, and settlement of plate is known. Now, you need to find the settlement of the foundation, which is given by this relation, and you need to put just numbers in this relation. What you have here? You have in this case let us say that Bf footing width, which is 3 meter, that means 300 centimeter, and the 60 centimeter, and then once you put all the numbers, this ratio comes. While using this relation, you need to understand that this square is coming most of the time, this square is missed out, and then you get the wrong answer. So, you get this 9.3 mm as the settlement of the footing. This was for the settlement of the footing is found out using this relation. Continue with this another example on the settlement, and we use the data of what we have discussed in example 3. That the question is that using the load test data in example 3, determine the allowable load on a 1.5 meter into 1.5 meter column footing. You have a square footing, but now the footing dimension is different. Earlier it was 3 meter by 3 meter. So, be careful, here it is 1.5 meter into 1.5 meter with its base at a depth of 2 meter. Df is also changed. So, df is 2 meter, and the permissible settlement for the foundation is 20 mm, and minimum factor of safety 3 is determined against shear failure. The weight of the soil is determined at the base of the test pit by the core cutter method was 2 ton per meter cube. So, these are the data given, and using these data we need to determine the settlement. The permissible settlement of the foundation is given. So, ultimately what is the question? Question is to determine the allowable load. What load you can allow here, and you know the allowable, for allowable load, when we talk about allowable load, you require a factor of safety which is also given in this question, that is 3. This will be required, that means ultimate load divided by the factor of safety will give you the allowable load. So, what we have in this solution, that the angle of shearing resistance of the soil, and this is done with the help of ultimate bearing capacity of the test plate QUP. QUP, as we have seen in the graph, that was the chart. Let me go back and then show you again the chart. So, you have this see here this chart, the QUP value is, this is where the tangent are meeting. This is no, this is not to the scale, but it is coming 24 kilonewton 24 ton per meter cube per meter square. So, what you have here for this case, the value of this QUP is 24 ton per meter square, and this is using the double tangent method, and which we have. Then this QUP is the ultimate bearing capacity for the plate, not for the footing, and we need to find the ultimate bearing capacity for the footing. For that, you know, when we talk about the plate, there was no surcharge on the plate, and the value of C equals 0, and the plate is a square plate. So, as a result, the ultimate bearing capacity is given by 0.4 gamma BP and N gamma. Here 2 terms are absent. One is absent because C equal to 0, and second term is absent because Q, which is surcharge, is 0. There is no surcharge. As a result, you get this value QUP. In this relation, QUP is known to you, but you do not know the value of N gamma. So, N gamma can be calculated, and N gamma comes 50. Once you know the value of N gamma, then you, using the back calculation, you find the corresponding value of phi, and for N gamma 50 correspond to phi equal to 36.5 degree. Once phi is known, then you can calculate for footing the value of NC and NQ, but NC is not required because C equal to 0, it is sandy soil. So, NQ comes out to 40. Now, using this data, we calculate the ultimate bearing capacity for the footing. So, here, because ultimately we need to find the net self bearing capacity. So, QNU is calculated from this relation, gamma df NQ minus 1, again 0.4 is coming instead of 0.5, because your footing is a square footing. So, 0.4 gamma B and gamma, but surcharge is there now. So, and surcharge will be gamma into df, and gamma is unit weight is 2 ton per meter cube, df is 2 meter. So, gamma df, this is q, and 40 is value of NQ minus 1. So, once you put all these numbers, then you get 216 ton per meter square. If you divide this simply by factor of safety 3, then you get net CF capacity as 72 ton per meter square. This was based on the bearing capacity equation, but we need to check from the settlement criteria also. And for the settlement criteria, what you have? The settlement for the plate, allowable settlement is given here. It is the reverse case here. Earlier, you have been given the load and you find the value of plate load test, this value of SP, but SP is not known here. Rather, the what is the maximum settlement which is permissible for footing is given 20 mm. So, we can find the corresponding settlement of the plate using this relation, and corresponding settlements comes out to be 12.8 mm, which is, and no, this is going to be less than the settlement, because footing is higher, the dimension of the footing is more compared to the plate, the settlement of plate will be less than 20 mm, that is sure. So, this comes out 12.8 mm. Now, for this 12.8 mm settlement, we determine the load intensity using what is the typically called the this methods by suggested by our researchers. So, in this case what you do, you use this chart back again, and in this chart see for 12.8 mm. For 12.8 mm settlement, you get from this, and here we cannot use this because this is out. If you 12.8 mm, your curve is out. So, this tangent which is asymptotic tangent, and this is a method suggested by Rao and Ramaswamy. So, you have and this tangent you meet this point and corresponding value you pick up this value, you pick up from this chart this value which is between 30 and 40. So, this is exactly 32 ton per meter square. So, for this value you get net separating pressure 32 ton per meter square. So, now you have two values, one value is coming from the bearing capacity point of view, ultimate bearing capacity which we have obtained in the last slide, that was 72 ton per meter square, and from settlement criteria 32 ton per meter square. Naturally, for safer design you need to use the lower value. So, the settlement criteria will govern the design, and this is the normally for the granular soils or the sandy soil, the settlement criteria is governing the criteria. So, your answer comes 32 ton per meter square as a allowable load intensity, and allowable load will be simply this intensity multiplied by the area which is 1.5 into 1.5. So, your answer is 72 ton. So, this is the final answer coming for this. So, if you compare example 3 and example 4, so like that these are like in first case you have this given the settlement of the plate, you need to find the settlement of the footing. In the second case, allowable settlement of the footing is given, you need to find the allowable load on this. Now, these all these example 3 and 4 was based on the plate load test. The last example which is based on the SPT data, and this is the like the SPT data, and I think I will complete in 5 minutes this one. So, what you have in this case, this is the figure, you see that this footing is given and b equal to 3 meter is the width of the footing, depth of the footing is 1.5 meter, that is from ground level to here. Now, when you want to find the settlement using the SPT data, you need to use the IS code, and the IS code suggests that find the average value of n below the base of the footing and up to a depth of 1.5 times of b or 2b. So, if you have the available data, go up to 2b, if data are not available, at least you need to go 1.5 times of b. So, here if we see b is equal to 3 meter and 1.5 times equal to 4.5 meter. So, data are available below this is 1.5 meter and this data is up to 6 meter, that means this depth is 4.5 meter. Below the base of the footing you have data up to 4.5 meter. So, this is enough data is available. So, what we do simply concept is here, you apply whatever corrections required corrections, the two corrections we already discussed in the last lecture. One was correction due to overburden pressure, another was due to dilatancy. Applying both corrections you get the n values, and these n values should be at an interval of 0.75 meter, that is the suggestion. And if the strata is changing, then you need to again get the n values. So, up to 0.75 meter, for example, the first 0.75 meter, then 1.5, then 2.25, 3, 3.7. So, these data are at every 0.75 meter. So, they are good data, and our n values will be below the base of the footing. So, we do not consider this data above the base of the footing. So, using this the calculation is done in the tabular form, which is on the next slide. But before that, the correction due to the overburden pressure is using this relation, and in this relation you need to understand the sigma naught is in kilogram force per centimeter square in this relation, not in kPa. So, let us use this relation which is given in the next slide. So, this is what we have already discussed, that average value between elevation minus 1.5 to 6 meter is considered for the calculation, and this enough data 4.5 meter equal to 1.5 b. So, data are enough. Now, first column is elevation which is given, second column is calculated simply gamma into h, where gamma is not constant, and you need to understand that gamma is given data is varying. Gamma for this layer, first layer is 1.8 ton per meter cube, for second layer 1 ton per meter cube, while third layer 0.8 ton per meter cube. And first layer is coarse-sand, then you have water table at a depth of 3 meter. Below water table up to 4.5 meter you have continuous coarse sand. So, that means the correction due to dilatancy need to be applied after starting from after 4.5 meter, not above that. And so, this is all the tabulation is given here. So, what you have, this column is ton per meter square gamma into h, and then if you divide by 10, then simply you get kilogram force per centimeter square. So, this is the value, and the third column is C n, which is the C n value is calculated from the equation which we have just discussed. This n f subscript f, that means these are the field values of the n which is directly measured in the field. So, n f multiplied by C n gives you the value of n in this corrected value, and this is corrected due to overburden pressure. Then you need to apply the correction due to dilatancy, but the correction due to dilatancy will start only from 4.5 meter, and that is also if your n values are more than 15, but all three values are more than 15. So, it will be you could see that this is applied 22. So, 15 minus you do have this the like 22 minus 15 7, you have this 3.5 plus this, so it will get 18.5. So, it will be somehow this will be 18.5. So, this can be applied and then seen. So, all these after corrected values. So, final values you get 1, 2, 3, 4, 5, 6, 7, and we do the average value of this number, and once you do this these 7 layers n values, so you get 18. So, to get this number we need to do so many calculations, and finally answer we got is only one number n. Now, if you got this value of n, then we can use the chart which is given in the IS code to get the corresponding value of 33. And the chart like here we can use either IS code, in this case we have it has been used by Peck and Hansen and Thornburn. So, the chart is given is here, if you see in the next slide, this is the slide Peck Hansen. So, what we using this chart for corresponding value of n, you find the angle of shearing resistance. N values are given here, if you see this, these are the n values. So, n are coming to 18, for 18 values of this is the n values here. So, if you have for 18 corresponding to 18, you get finally the number for angle of internal friction. So, angle of internal friction is given and the down. So, for corresponding, and this can be done using the IS code also. So, somehow here it has been done using this. So, for this n value of 18, phi obtained is 30 degree. Once you obtain phi equal to 30 degree, again we calculate the value of nq and n gamma, which is from the chart which is given by IS code, and the IS code 64039. So, this is nq and n gamma, nq and n gamma for the corresponding value of phi, you read the value of nq and n gamma from this chart, and this is given here, which is coming out 22 and n gamma. And here the value of C is given 0. So, we do not need the value of NC, and finally using this relation you get the value of net ultimate bearing capacity. Here this is according to IS code. So, we need to you need to apply the correction due to the shape factor and depth factor also. The corrected value of shape factor is here, which is BA by L, where B is given B and ratio of L is given 3 by 5, and so this once you put the number SQ comes over 1.12, this is 0.76, and when you apply the correction for depth factor, which is given by the according to IS code 10 45 degree plus 5 by 2. So, once you put all these numbers, phi is given 33 degree calculated, and you come out to be 1.09. Once you put this calculated number in this equation, and before that calculate the value of W dash also. The correction for water table for W dash is applied here. So, first you have this one 0.75, which is I think already calculated the correction for water table. Yeah, this has been not shown, but you can have W dash is because the water table is C location of water table. Let me show you the location of water table is coming in this slide here. This water table is here. So, this water table is at a depth of 1.5 meter, that means from the base of the footing. So, that means it is if it would be 3 meter depth, then no correction is applied, but so that means this depth is what we called dW dash, and dW dash is coming 1.5 meter. So, your W dash will be 0.5 plus 1.5 divided by 3 and then so once you work on this, so 1.5 divided by 3 into 0.5. So, you get 0.75. So, the value of W dash comes out 0.75. So, 0.75 is coming here in this calculation for the correction due to water table. If you see in the next slide, it is 0.75. This is the water table correction. Putting all the numbers, you get the value of Q and U, that is net ultimate bearing capacity. Factor of safety was given 3. So, this is the net self bearing capacity from the bearing capacity point of view. And for this QNS, from chart for settlement, we get n equal to for now let us see the settlement. There is chart in ICE code settlement which we have already discussed in the last lecture. For n equal to 18 and b equal to 3 meter, the chart which is given for the settlement, we get the value of settlement for 1 kilogram force per centimeter square, that is 10 ton per meter square, equal to 0.015 meter, that is 15 mm. So, 15 mm settlement has been obtained, and the correction for water table we already discussed 0.75. So, for settlement, the settlement will be higher due to the correction of water table, and it comes out to 20 mm. And for this 20 mm settlement, you find the corresponding value for Q and P, because when settlement was 40 mm, then you have this allowable settlement is 40 mm. So, that means you can have higher instead of 10 ton per meter square, your this intensity could be double of that. So, 20 ton per meter square. Now, out of these two numbers 20 ton and 38.7, the minimum the lower one will govern, and your final answer is this Q net 20 ton per meter square is the this net loading intensity from this. So, this was an example on this using SPT data, and using SPT data we have done using from both criteria, from bearing capacity criteria as well as from the settlement criteria, whichever is the lower value which will govern the design, and the answer comes net ultimate this intensity allowable is 20 ton per meter square. So, this I think we have discussed quite a number of examples. First two examples, one on bearing capacity, another two was on settlement, and the third one was on bearing capacity as well as settlement, but last one, fifth one was for that for SPT data. Now, bearing capacity settlement is completed. So, now next lecture we will talk about combined footings on that. Okay. Thank you very much. Thank you for your kind attention.